Hello everyone, welcome again to the channel. My name is Amos from Symmetry Acoustics. Just as I promised in the other video, today I'll be sharing with you a few tips on how to bring down the room modes and how to manage them so that you can have a room that is bearable to work in if you're mixing or you're mastering, especially for home studios. So before we proceed, there's something I introduced in the other video. If you've not watched it, I'm going to link it down. You can find it, and it talks about how small rooms have problems with the room model issues and their causes. So today I'm going to talk about room volume. The other video was about room dimensions or room ratios and how they are responsible for room model distribution. Room model distribution is how the room modes are distributed in the room and their locations, and that is where the room ratios are responsible for that. So in today's video, room volume will determine how early we start to deal with the room modes in the room, and that is a very good explanation as to why when you look into large spaces like auditoriums and churches, you never see any strapping in those kind of environments. What you see is broadband absorbers or general 2-3 inches panels all around the surfaces. So why is this so? So that is where we go back to shorter frequency. Shorter frequency that I normally talk about is the crossover point, is the point at which the sound starts to resonate in a room from being reflective. So like in the case of the model room we used in the previous video, we used 12 by 10 by 8, which is the length, width and height in feet. And that is where we now find shorter frequency to be at 279. That's literally lower mid-range. That is not a base area. That is the lower mid-range, but because the room is so small, the room starts to see that as a base, and that is why small rooms have very big problems in controlling the low frequencies, because when you start to treat these low frequencies way earlier, then you have to spend so much money and modules to be able to get all the way to 50 hertz. On the other hand, large spaces have enough dimensions for the frequencies and the wavelengths to travel and fit in, so they normally have their shorter frequency shifted to the lowest of the end of the spectrum. And in most cases, if you look in, you find that the shorter frequency of large spaces like auditorium and performance venues start at almost below 20 hertz. Some start as even as 16 hertz, and that is good in one way, because we don't have to drill with room modes anymore in that case, because we can't hear anything below 20 hertz in most cases. So the problem with that is that we have to deal with ridiculous amount of RT60 readings, which is reverb time, and these spaces sometimes have reverb time of up to around 5 seconds, which is very ridiculous and crazy. It's almost impossible to hear each other in that kind of RT60 reading. So this kind of inverse relationship between size and RT60 and shorter frequency, whereby if the room is smaller, we start dealing with the room modes way earlier at 300 hertz. That is way earlier, and we don't have reverb time, excess reverb time in small rooms. So that's why if you take your readings using Room EQ Wizard, the software automatically translates the readings into T20 or T30, because we don't have true reverb that takes place in this kind of small rooms. So how do we treat the room modes? So number one, we have to understand how low frequency behaves in this kind of environment. When low frequency are produced from point source in small rooms like home studios, which in this case was what we're talking about, two things happen to this low frequency. We have molecular velocity, that is the speed of air molecules in the air as they are pushed towards the boundary surface, and then we have what we call sound pressure level also happening at the same time. So you realize that as you look at this figure here, these are proven scientific research that were done over the years way back. You find the sound pressure level of low frequencies is always very high at the boundary surface, that is the room surface, and that explains why if you walk across the room and you head towards the rear wall or the front wall or the side walls, there's high bass in those areas, while if you move towards the center, the bass kind of diminishes and dies down. That explains why the SPL is so high towards the surface. So what happens to the molecular velocity? Molecular velocity is actually low at that very point. So there's inverse relationship. They are 90 degrees out of phase, whereby the pressure is high at the boundary surface, but the molecular velocity is low at that point. And that takes us to a very interesting also concept, which we call a quarter wavelength principle, or a quarter wavelength rule. It's a very straightforward thing, so let me explain to you what it means before we proceed. So a quarter wavelength rule means that at a quarter the wavelength of any frequency, if you place a panel at a quarter the wavelength from the boundary surface, you are able to reduce the magnitude of that frequency significantly, because that is where the peak of that wave is. So in this case, let's calculate how we can be able to reduce 50 Hertz using a quarter wavelength principle. Let's now calculate it. Okay guys, now let's get into the calculation and see how thick our panel need to be able to absorb 50 Hertz. So how do we do that? So let's calculate the quarter wavelength of the 50 Hertz. So we take the speed of sound, in this case 1130 feet per second. Let's divide that by 50, and what we get, we divide it by 4. So my calculator shows me that it's supposed to be 5.6 feet. So it shows that for us to absorb 50 Hertz using porous absorbers, we need our panel to be 5.6 feet thick. That is crazy, because that is almost half of our home studios. So we can't be able to do that. It's not practical in most cases. So the question is, how do we deal with these kind of frequencies to bring them down? Now this is where we have technologies like membrane absorbers or pressure-based absorbers. These pressure-based absorbers work slightly different in that they are created to have low pressure inside them. They are literally sealed boxes with maybe absorbent material and some layers of membranes, that if you place them at the point of high pressure, then the sound or the high pressure sound at that point will be able to be reduced drastically. So that is how they function. We have Helmholtz resonators, we have things like membrane absorbers and diaphragm absorbers. They are kind of technical products, and they are very expensive for a lot of home studio guys. So in this case, I would advise that if you are on budget, then let's take the common route that is very familiar to a lot of guys, and that is the porous absorbers. So the question is, how do we deal with room modes using the porous absorbers, now that the membrane absorbers are slightly more complicated in most home studio kind of scenarios? Before we proceed, we need to locate where the room modes are that can be able to be controlled using the porous absorbers. Most porous absorbers that I'm aware of work around 70 Hertz in most cases, and the performance then comes down below 70 Hertz because of the kind of thickness that is required to absorb the lowest of the low. So you need to allocate the location of the best frequencies. In this case, if we take a look at the Ambro calculator and how it shows the location of the room modes, you find that things like 70, 80 Hertz, in most cases 90, which we call tangential modes, are normally located on corners. And that's why a lot of companies out there advocate for placement of bass trap on corners. That is one of the reasons to take care of the tangential modes, because you can do that with the porous absorbers and get a pretty decent outcome. Now, how do we deal with frequencies that we cannot control using the porous absorbers? If you can't have pressure-based devices because they are costly, and even if you decide to design one by yourself, there's a high chance it won't work. They need kind of technical approach to them. So my advice would be, what I would do as a home studio guy, or any advice I would give home studio guys, number one, before we rush to room EQ softwares to EQ our room, ensure you treat high frequencies well, mid frequency and low frequency, the lowest you can get, and whatever remains, that is practically around 70 Hertz and below, you're able to EQ the room at that point, because you are sure of you have minimal problems to deal with when you treat all the way to 70 Hertz. The downside with the room EQ is that it will not get rid of the room modes. What it will do is it will enable you to make the right decision only at your sitting position, because that's where you take the measurements, and the rest of the room will just remain like that. The good thing is that it doesn't cost so much money to be able to correct the frequencies that the room is trying to boost. So that is basically how you deal with the room modes in this kind of small rooms, especially low frequencies, and you're able to get a pretty decent sounding room without spending a fortune. So hope the video was helpful for you guys. Thank you for watching. Like, share and subscribe.